Welcome to this month's ABC UTC Monthly Webinar. My name is Mary Lou Rawls-Newman. I'm Director of Technology Transfer at the ABC UTC and will be moderating today's webinar. I'll be assisted by Ali Javed, PhD student at FIU, who is managing the web room. First, a few slides on our upcoming 2022 International ABC Conference, fully in person this year on December 7th through 9th in Miami, Florida. Please visit the conference page on the ABC UTC website for more information and to register. As in the past, conference and workshop attendees will receive certificates of attendance. Also, for those of you in Florida and New York, FIU is an official sponsor of continuing education. 4 half-day pre-conference workshops will be held on Wednesday, December 7th this year. Steel bridge design and fiber reinforced polymer composites bridge design workshops will be held in the morning, and pre-stressed concrete bridge design and non-proprietary UHVC workshops will be held in the afternoon. We very much appreciate our workshop coordinators and presenters. For more details, please go to the website shown on the screen. In this month's news presentation, we'll feature the steel bridge design workshop. Topics in this workshop include analysis, as you can see here, steel bridge design, best fabrication practices, and available resources. Details on all 4 pre-conference workshops are available on the ABC UTC website, so you can get lots more information on what you'll be seeing there. Opportunities are also available for exhibit booths. If interested, please go to the website shown. We hope to see you in December in Miami. Our presentation today features the Hawaii Department of Transportation's Waikoko Bridge Replacement Project. We're pleased to welcome our presenters, James Fu, State Bridge Engineer with the Hawaii Department of Transportation, Eric Matsumoto, Vice President of KSF Inc., and Gary Iwamoto, Director of Construction Services with KSF Inc. Would like to also introduce our Q&A session moderators, Paul Lyles, former Georgia State Bridge Engineer, and Jugesh Kapoor with WSP USA, and formerly State Bridge Engineer at WashDOT. We'll now begin our presentation. James?
Good morning. My name is James Fu. I am the Hawaii DOT State Bridge Engineer. Today's presentation will be about Hawaii DOT's Waikoko Bridge Replacement Project. During this presentation, our structural consultant, KSF Incorporated, will be here for technical support. KSF completed the design for the new Waikoko Bridge. With me will be Eric Matsumoto, who is the Vice President of KSF, and Gary Iwamoto, who is Director of Construction Services for KSF. Hawaii currently has about 1,360 bridges in the state. The average age of our bridges is nearly 70 years old. For your information, the Hawaii DOT, our Bridge Design Office, is managing many programs in our state, such as the Bridge Seismic Retrofit Program. We are managing the Bridge Load Rating Program, where we must meet a federal mandate to load rate all of our bridges for SUVs by December 31st, 2022. We are also managing a bridge crash testing program, where we are crash testing our custom Hawaii bridge rails per MASH 2016. We're also replacing many of our destination sign support structures. And one of our main things that we're doing is that we're managing our bridge asset management program, where we must meet transportation asset management goals of 20% good bridges and 2% poor bridges. And one of our critical tasks is to address critical bridge findings. Hawaii has a unique situation from other states because our highways wrap around the island like this, and it's usually called a belt road system. For most cases, because of this belt road system, if a highway is closed for some reason, residents must use an alternate route, and most times they need to drive great distances to get their destination. For example, when Mary Lou's called me about a month ago, there was a 30-inch water main break near Kaava, on the north shore of Oahu. The water main break took out a portion of the highway and closed Route 83 along here on the north shore. This meant that anyone traveling by car to the other side of the bridge, Mkaava, would have to take this alternate route this way. To get to the other side of the bridge would take about 87 miles and over an hour to drive. So this is very typical of the situation of our highways. But sometimes we have a situation where if the highway is closed, there is no alternate route. And this leads us to our presentation today. We want to talk about an area on the north shore of Kauai. Here's Kauai, where the highway was completely closed during a major flood emergency. On the island of Kauai, Route 560 runs along here on the north shore. And Route 560 ends at Haena. Note that there is no highway beyond Haena, so there's only one way in. So back in April 2018, there was a huge rainstorm on the north shore of Kauai. Heavy rains occurred between April 14th and 16th of 2018, which set a national record of 49.69 inches of rain in a 24-hour period of time. The previous Hawaii record was 38 inches. These heavy rains created many landslides on the north shore of Kauai, which closed the highway. Route 560 along here, like I say, was shut down due to the landslides between Waikoko here and Wainiha. See Wainiha here. And as I mentioned before, to get into this area, Route 560 is the only access to Wainiha and Haena. Traffic was slowly opened to one-lane traffic after a few weeks. Here we're showing large sections of the roadway were blocked by multiple landslides. And large sections of Route 560 were literally washed away. This is a picture of the old Waikoko Bridge. Note that this bridge was in poor condition even before the flood emergency. You actually can see here, these are the concrete bridge railings, and they are already sunken. So what they did was they added a rock bridge railing on top of that. They filled up the area that was sunk, and that enabled traffic to cross the bridge. So this is done. This was before the emergency. Again, this is a picture of the existing bridge. Note the concrete sunken bridge railing here with the added rock bridge railing on top of it. The floods damaged the bridge, and in order to open the highway to traffic, the bridge needed to be replaced as soon as possible. So the Waikoko Bridge was built in 1912. It is considered historic and on the National Historic Register. And like I said, it was damaged during the flooding of April 2018. Hawaii DOT decided to replace the bridge after reviewing the option to construct it with a full highway closure for one weekend. This is a timeline of the Waikoko Bridge replacement. The design of the bridge took approximately one month. As I mentioned, the floods occurred in April 2018. Design started about July 2018. Took about 1 month. An additional 2 months were needed for environmental permitting and consultations. In about September 2018, the contractor started work on this project, but he was actually in the field in this red portion for 304 days, as shown here. During those 304 days, the actual bridge construction was from May to June of 2019. And within these 81 days, there was a 3-day full highway closure occurred from June 13th to June 16th, 2019. And the bridge was open to traffic. The new bridge was open to traffic on June 16th, 2019. After the bridge was open, there was additional work for the contractor to restore the utilities, do approaches to the bridge, and restore the utilities. The further discussion here, we're going to talk mainly about this 3-day weekend highway closure. This is a plan view of the replacement bridge. This bridge is a one-lane simple span bridge, and it's hard to see here, but it's 70 feet long. We'll go over the construction sequence later, but note that there were micropiles. Micropiles were installed at the 4 corners of the bridge. The abutment pile caps were then connected with a transverse grade beam here and here to connect the 2 pile caps. The bridge girders were actually the bridge railings, and they were L-shaped, as I'll show you later. After the girders were placed, transverse precast concrete planks, shown here, were placed and supported by the bridge girders. Here's an elevation view of the new bridge. Note again that it's simply supported. There's no piers in the channel. Micropiles were here. They were connected to the abutment pile cap here. And here's the transverse grade beam that goes into and out of the page. Here's the bridge girder / bridge railing. And here are the precast planks, which were supported by the bridge girders. Here's a cross-section view of the bridge. Note this is a one-lane bridge. It is 14 feet wide. Note the bridge girders. They're L-shaped. And here are the transverse precast concrete planks. Like I said, they were placed transversely. After the precast planks were placed, a cast-in-place concrete curb was placed to connect the precast planks to the girders. Here's a picture of the casting yard for the precast concrete planks and girders. This casting yard was in Lihue, and it's about a 40-minute drive away. Here on the left, it's a little hard to see, but with this flat area, that is a casting for the precast planks here. And here, this is a casting for the precast L-shaped girders. The precast planks, there were 17 precast planks and they were match casts. They were approximately 18 feet long, or 4 feet wide, and about a foot thick. Concrete strength about 6 KSI. And shrinking corrosion inhibitor and shrinkage reducing admixtures were used in the concrete mix. The reinforcing steel for the precast planks, they were grade 60. There were 5 corrugated polypropylene ducts for the post-tensioning. As you can see here, the white tubes are the post-tensioning ducts. And then also at the ends, on the ends of the plank, were precast segmental duct couplers here. And they were used to also help tie the planks together. Here's a picture of the reinforcing for the precast concrete girders. Note the L shape of the girders. Here's a picture of the completed girders. And again, note the L shape, which provides a ledge for the precast planks. Due to hauling considerations, the precast girders needed to be spliced. And here's a picture of the closure joint to join two segments of the bridge girder. I will now go over the construction sequence of the new bridge, and I'll go all over this in the next few slides. So don't worry about reading this. And before the weekend closure, note that this is a transverse or cross-section look at the bridge. This could be the upstream, this could be the downstream. The bridge girders would run longitudinally and coming at us into and out of the page. So first, micropiles were installed. Then the abutment pile caps were poured. And then the transverse grade beams were installed to connect the two abutment pile caps. As I mentioned, this is before the weekend closure. As mentioned before, micropiles were installed at the four corners of the bridge, and this slide shows the details that were used for the micropile. The new bridge would be located here. And note that this bridge is a temporary bridge. It's a temporary pedestrian bridge and would be removed after construction. As mentioned before, micropiles were installed at the four corners of the bridge. And at this corner, you can see that the drill rig was being done to drill for the micropiles at that corner of the bridge. Here's a picture of the abutment pile cap. And you notice that the existing bridge is right here. See the existing concrete bridge railing here and the stone railing, bridge railing here, this existing bridge. So after this concrete pile cap was poured, the concrete grade beam going this way would be poured to connect the two abutment pile caps. So the micropiles, the pile caps, and the transverse grade beams were installed before the 3-day full highway closure. During the 3-day weekend closure year, the precast girders were placed, the L-shaped girders. Then temporary tension ties were installed near the bottom of the precast planks. Then temporary compression struts were installed near the top of the bridge girders. Here's a picture of the contractor setting the precast girder, which is right here. Again, here's a picture of the contractor setting the precast girder. Note the L shape of the bridge girder. How do the precast bridge girders sit on the abutment pile cap? The abutment, the bridge girders, actually here is a plan view, and the bridge girders / bridge railings run in this direction. Again, this is a plan view. And the bridge girders actually sit on elastomeric bearing pads. The elastomeric bearing pads are 1/2 inch thick. They have dimensions of 2'6.5" here and 1 foot. So the yellow is the elastomeric bearing pad. The blue are concrete creep blocks, which helps the bridge resist lateral loads. This is a picture of the removal of the existing bridge. See the existing bridge railing here and here? And note that the bridge girders were already in place. This is another picture of the removal of the existing bridge here. And note, the bridge railings are here. Here is a picture after the existing bridge was removed and the girders are already set in place. Here's a picture of the tension ties at the bottom of the precast plank where the precast planks would be placed. Again, note the L-shaped girders. Here's a picture showing all the tension ties, the temporary tension ties have been installed here. The tension ties are all installed. Now the first compression strut, this timber compression strut is placed here against the bridge railings. And here, the contractor is setting the first precast plank. After the tension ties were installed, the precast planks were installed. And wedges were installed between the edges of the precast planks and the face of the girders. The wedges were installed to ensure intimate contact between the precast planks and the bridge girders. Then additional compression struts were placed. Then the precast planks were post-tensioned longitudinally. And once they were post-tensioned longitudinally, the wedges were removed. Here's a picture of the precast planks. Note the post-tension ducts here, typical post-tension ducts that would tie the planks together longitudinally. Again, here's a picture of the precast planks. Note that the workers are applying an epoxy compound to the faces of the precast planks so that they would bind together. Actually, you can see the epoxy right here. Here's a picture of the typical post-tension duct coupler. The intent is that when the transverse planks are placed, the post-tension duct couplers would again help lock the planks together. Here's a picture of the contractor setting the precast planks here. And setting another one right here. Here's a picture from under the planks. Note the tension ties here. Note this is the precast plank. Note the post-tension duct couplers here. And although it's hard to see, you can, if you look close enough, you can see that the epoxy is on the coating between the planks. Here's a picture of all the precast planks in place. Here's a picture of the workers installing high-strength bars through the post-tension ducts here. Again, these are the workers, and now they're stressing the high-strength bars. Notice the 5 high-strength bars, 1, 2, 3, 4, and 5. The post-tensioning would squeeze all the planks together. After the workers stress the high-strength bars, you can see the epoxy oozing out from the top of the deck. Next, grout was placed beneath the precast planks and within the 3-inch diameter blockout. Next, concrete curbs were installed with downturns at the end of the bridge. Next, girder caps were installed. And finally, the compression struts and the tension ties were removed. A critical part of this design was a cast-in-place concrete curb, which again is right here. Why was this critical? Because this concrete curb allowed dowels to be placed, which connected the precast planks to the bridge girder. This is your L-shaped girder. After the concrete cured, this allowed the temporary compression struts and the tension ties to be removed. Here's a picture of all those dowels in the concrete curb. Here's a picture of the workers placing concrete for the concrete curb. So after the cast-in-place curb was installed and the temporary compression struts and the tension ties were removed, the bridge was ready to be open for traffic. The Waikoko Bridge was open to traffic on June 16, 2019. Before this flood emergency, the designer, KSF, was already looking into a bridge replacement concepts due to a possible design build project for the bridge, as you can notice with the sunken bridge railings show. That made it easier to go to final design very quickly. Also, the state of Hawaii issued a state emergency procurement for this project, and the contractor and we had resources to do the work, and we could proceed as soon as plans were available and material was procured. We're now going to show a short, this is just about 2 minutes long, time-lapse photography of the 3-day weekend closure. Gary Iwamoto, Director of Construction Services of KSF, he'll jump in and kind of show you what happened.
Okay, so starting at 8 o'clock on Friday night, they started setting the setting the girders, and then started excavating out the old bridge. And once that was complete, they moved in to start setting the planks. And that continued until all the planks were set. And once the planks were all set, the post-tensioning operation took place and the grouting of the ducts. And then the curb work and the railing cap work was done, and basically that completed the primary work on the bridge. Once that was complete, the work on the ramps, the temporary ramps, and the end post protection devices were installed, and to get ready for the bridge opening once everything was cured out. And so this entire process took about 56 hours from Friday at 8 p.m. to Monday morning at 4 a.m. And once everything was cured and everything was cleaned up, at about 4 a.m. in the morning, traffic was allowed to cross the bridge, and then work continued to restore the entire site and to install a permanent roadway and relocate all the utilities that were previously relocated to allow this work to continue.
Okay, that that basically wraps up our presentation. And if there are any questions,
All right, thank you very much, James and Gary, for sharing your ABC work with our participants today. We're getting lots of questions coming in, so participants are interested in your project. Very interesting. Paul and Jugesh will now moderate the Q&A session. Paul?
Thank you, Mary Lou. Yes, we had a number of questions that came in, and we've got it kind of broken down into design questions, construction questions, and cost questions. And we have a bunch of come in, and I think there'll still be some more coming in. The first thing I have is more or less on design, and this is more a hydraulic question. The first one was, how was a future flooding event considered in the new bridge design?
So for future flooding, we did have a civil engineer on this project who ran the hydraulics and for the 100-year flood. So we do have the freeboard for this new structure. If you saw the previous slides from James, the original bridge had collapsed, so it was blocking most of the waterway. So the new bridge expands that waterway and addresses the 100-year flood.
Okay. The second question, this is sort of hydraulics, but it says, was the bridge designed for a tsunami loading?
No, it wasn't. But we did look at the stream flow, and although we had the freeboard, we did put that stream flow on the structure, on the face of the structure, and that load was transferred into the foundation.
Okay. Do y'all have tsunami loadings at all in Hawaii? I mean, I know you have them, but I mean the events. But is that in y'all even consider that? Just curious.
we will be considering it. I know there's a new guide, AASHTO guide for design of bridges for tsunami. I'd like to bring in some ocean experts on that because it's, yeah, we may need some help with some ocean engineers to implement it.
Okay. All right. Here's a question that came in during your presentation that are also maybe hydraulics, but the question was, could you build elevated bridges in the flooded sections to help with the traffic during flood times?
So I think for each situation is a little different based on the site conditions. So we usually have a low profile bridge in these low flood zones or flood zones, and it's typically planks. If we were to elevate the bridge in this area, then we would have to address the approaches, which would take up a lot of the roadway, and we have to look at the driveways and other roads that tie into this main roadway.
Okay. There was a question here about was anything done to prevent the bridge from maybe floating off the fat structures in another record flood?
We did look at the bridge floating, but this bridge is it won't float. It's very heavy. So if you compared it to a girder bridge, which is actually deeper, it's going to be heavier because it's a solid slab piece, and those L shapes are pretty heavy in itself. So it's not going to float away, and the weight helps us in this instance with flooding. Seismically, it's probably not as good. However, as James showed you from the picture of the Hawaiian Island chain, the hot spot is which is located at the Big Island or the southeast part of the Hawaiian Island chain. That's where you have the most seismic activity. Kauai, or this actual location, is on the north end, or the northwesternmost major island in the chain. So it has the lowest seismic activity there. So seismic was not a big factor. And so going back to the original question, the bridge is heavy, so it's not going to float away.
Okay. Next question. Again, we have a series of questions on the your beams, and the first question regards that would this be considered a fracture critical structure?
No, I do not believe it's fracture critical.
With just two girders?
Fracture critical is defined we just took a course in fracture critical. Actually, to define a fracture critical element, it has to be steel.
Yeah.
Because that's sudden failure. These probably wouldn't be a sudden failure.
Yeah, I got you. Okay. The next one, what factors were considered for redundancy since this system is akin to a steel through girder bridge?
So this area is low speed. It's a one lane bridge. But we did design the girders or the barriers for impact, which was a TL1. We did place a curb in front of the railings, which at this low speed we can consider it unmountable. For your redundancy, it's actually in the details. We have added capacity in the railings with compression bars built in the railings. We also have additional steel in the curb that we did not use in the design of the L-shaped girder.
Okay. With the railing as the main structural element, were special design or details used to address potential impact from traffic? You might want to comment on the low speed and one lane of traffic is pretty small volumes. But go on.
Yes. So yeah, going back to that, the railing, it was designed for TL1 loading. It's very low speed, and I don't believe the traffic volume is high. But we did design it for that impact load. And again, there's that a curb in front of the railing that is unmountable at these low speeds.
Okay, that impact loading, is that just a transverse loading on the railing? Okay.
Yes.
All right. And that was the questions, if the girders are structural stringers, are they serving as traffic barriers? And that's what they are also. Then let's go on and we'll look at some other questions. Here's one that says, on slide 22, why was such a large closure pour used for the girders?
We use well, for one thing, the girders, we have it coming in 3 pieces. James showed you the casting yard, which was about 40 minutes away, and so there are limitations on the transportation of these girders to the site, and so the girder lengths or sizes were dictated by those limitations. And for this closure pour, we did locate all of the splices, the couplers, for the contractor, so that he could pour it without too much congestion. But yeah, the splices were the 4-foot splices were just based on those factors.
Okay. Now you use the 6,000 psi concrete in the closure pour?
Yes, we had 6,000 psi concrete with corrosion inhibitor and SRA. After the girder pieces were transported to the site, so close to the bridge, it was spliced, and it wasn't spliced in place, but it was close to the bridge in close proximity. And once it was closed, then it was ready to be picked and placed into its position along the existing structure.
Okay. We had a question that came in. Was the casting facility, since you're talking about the closure pour, but was the casting facility casting the beams, was the casting facility an existing facility, or was it created specifically for the project?
It was created special for the project, and the site was selected because it was readily available for the contractor.
Okay. Now we had a question here that came in during the presentation about the tension ties, and were they part of the permanent structure, or if so, were they galvanized or made out of stainless steel?
If this is pertaining to the rods that were placed
Yes.
on the bottom, those were temporary ties.
Okay.
For the girder, it's an L shape. So when we're placing the planks, there's a eccentric load, so the girder wants to turn in towards the roadway. That's why we had the compression struts at the top and the tension ties at the bottom of that ledge or in that ledge. So if it wants to turn this way, the couple would help resist it.
Okay, but those were temporary, you said.
Temporary, yes.
Okay. The next question we have, this was came in during your before your presentation, was corrosion resistant rebar considered or used in the project? It looked like regular black bar. I think y'all mentioned that early.
It is regular black bar. We would actually wanted to use the A1035, otherwise known as the Chromex, with the 9% chromium. However, we couldn't get it in time, so we did proceed with the black bar. We do have for the dowel that's coming out of the ledge of the girder into the plank, that is the 2205, the duplex stainless. To address corrosion, we do have the Cortec or the corrosion inhibitor in all of our concrete, and we also have a low water cement ratio. We specified 0.4 water cement ratio max. However, it did come in lower than that.
Okay. Were there any other provisions incorporated to address corrosion? You mentioned some corrosion inhibitors.
Yes, we did use the Cortec MCI in our concrete. We also included it in the grout for the post tensioning that surrounds the post tensioning rod within the duct.
Okay. And the next question we have, final question in the design section, was: is Hawaii DOT considering more ABC projects given the small outdated bridges on the islands? They mentioned Haliwa. I can't pronounce it. Haliwa. Yeah.
Yeah. Well,
Yeah, so we're looking at a slide-in bridge that's going to be happening in another couple months, and more we're looking at ABC type bridges to replace existing bridges because the state DOT wants to minimize or eliminate temporary bypass roads because you need to encumber right of way, and it's very difficult to get those areas to put in temporary bridges. So we're looking more and more for weekend type closures to install new bridges. And like I said, we'll be doing one in a couple months, which is a slide in.
Yeah. Okay. Let's look at some construction questions. And we've got a bunch more questions that have come in once we started the question and answers. So we'll try and move on along. What was the biggest engineering challenge the contractor had to overcome that wasn't designed by the engineer of record? Any thoughts on that?
I think most of the engineering challenges were designed into the project with lighter sections or lighter pieces to be put together on site, and that could be handled with equipment that we could strip down and get over the existing bridges, because there's a 15-ton weight limit for most of the bridges coming in. So But the biggest challenge really was dealing with heavy pieces of precast, pieces, in a very short period of time that we had. But as you could see in the time lapse, there was a lot of time where everything just sat. So at the end of the day, after all the planning and everything was done, everything went, fairly smoothly, and we had a lot of time left for the bridge to just simply cure and set, and all the temporary, all the permanent pour stuff to set, and before it was open to traffic.
Okay. We had a few more construction questions here, but was there difficulty erecting the planks around and among the compression struts? That was on slide 43.
No. So you can't see it, but it's offset, so it's no problem.
Okay. Question here about how was the grade beam poured prior to closure of the bridge and roadway?
There were temporary nighttime closures where they were dug out and rebar was installed and the beam was poured. There was
Okay.
a number of nighttime closures to do some work on the bridge to get it ready. Non-peak hours in the middle of the night.
All right. Here's the question about, could you speak on the selection of the epoxy to join the planks regarding the work window, and how was it prevented from hardening prior to application of the post-tensioning?
We followed the segmental bridge typical techniques for this application, and we used the Sika 31 SBA SBA slow mix, Sikadur 31 SBA slow set. So we did have a large window that we could apply it to the planks, to put it in place and squeeze it. And as you could see from James's slide that showed the epoxy coming out of the top of the plank, that's how we knew that it was still behaved like we expected it to.
To work. That's fine. There was another question along that same line about do you know what the setting time of the epoxy was between the planks?
We had 8 hours to from the time we applied it to post tensioning, and it was well within that period.
Okay. All right. I got a question here about with the tension ties. Let's see, that was the one we asked about the permanent structure. The question was, let's go to a cost question. And what were the temporary bypass costs and benefit for the project? I don't think you really ran a temporary bypass, did you? Didn't you run the traffic over
we
the
did not.
existing bridge?
We did not. There was a CFL project that was going to put in a acro temporary bypass road. That temporary bypass was estimated at between 10 and 15 million to go upstream of the existing bridge. So that work wasn't done, but
Okay.
it was quite involved because you had a number of issues related to drainage that was coming in on both sides of that upper area, upstream area. It was coming in both from the left and right side, and this bridge itself ended up costing somewhere in the neighborhood of about 3 million. So that temporary bypass was eliminated, and the cost for this weekend closure and some of the inconveniences that occurred that one weekend, I think the state was very pleased with the cost that was spent.
Okay. Got one more question here and then I'm going to turn it over to Jugash because we've got a whole lot of questions that came in during the question and answers. And this one, was there a specific type of high early strength concrete that needed to be used for the curbs? And that was there any specific?
Yes, we did use a high early strength concrete that was able to achieve 2,500 psi in 3 hours.
Okay, that gets us through the presentation questions, and I'm going to turn it over to Jugash for the questions that have come in during the question and answer session. Jugash?
Thank you, Paul. So the first question that came in during the webinar is, it's not the first, but the first one I'd like to ask is, was there difficulty erecting the planks around or among the compression struts?
That was
It was on slide 43.
No, like I said, the compression struts are offset from where the planks go, so it's not a problem.
Okay. Next question, was the grade beam poured prior to full closure of the bridge and roadway?
Yes.
Next question, can you speak on the selection of the epoxy to join the planks regarding the work window? How was it prevented from hardening prior to application of post-tensioning?
So we used that Sigadur SBA31 slow set, and we were able to complete the task of placing the epoxy on the planks and stressing within that window.
Okay, thank you. Next question, what was the setting time of the epoxy between the panels?
So we had an 8-hour window.
Okay. Was there any specific type of high early strength concrete that needed to be used for the curbs?
Oh, sorry. I think I answered this one earlier, but the high early grout was between the plank and the girder and beneath the plank and the ledge. But for the curb, we did not. Sorry if I understood the question earlier, but the curb we did not. But we did have corrosion inhibitor, shrinkage reducing admixture in the curb concrete, which was also 6,000 psi.
Okay, thank you. What is the ADT on the bridge?
I'm going to check that. I looked at the recent, couple of years ago, it was 33,300. But I looked this morning and it was 8,000. I've got to check into that. I can't see it being increased that much. I'm thinking it's
Okay.
more somewhere around 3,000.
Okay, thank you. Just a follow-up question on the epoxy. Did you use normal or slow set epoxy?
Slow set.
Okay. Next question, what were the design considerations for the tension ties and compression struts? How does the cast in place curb function to replace them?
So if we looked at the entire construction sequence, the initial phase would be setting the girders and then placing the planks on it. So when we place the planks, it wants to turn inwards towards the roadway. So the compression strut, the temporary compression strut on the top and the tension tie on the bottom would help to resist this overturning with this couple for the compression strut and the tension tie. Once the planks were placed, we had wedges that were placed between the girder and the plank to for added compression as a compression strut. So it's a belt and suspenders with the timber that you saw going across. But once we for that curb that's shown in number 12, that eventually ties the the girder to the curb and the curb to the plank, so that at that joint there's a complete resistance at that point. So once the curb hardens, then we're able to take off the compression struts and the tension ties at the bottom. So if we look at just that juncture between the plank or the plank curb and ledge, there's that stainless steel dowel that goes from the ledge into the plank. It also extends into the curb, but that has the resistance at the bottom. And we also, so we have the curb and the top of the plank providing that, replacing the compression strut or the wood that goes across the top.
Okay, thank you. How long did the whole bridge replacement take, and what were the lessons learned?
The
You
entire
showed that
time it took
go
about
ahead.
56 hours to complete the weekend closure. And I guess part of the lessons learned was that I think that it could be done in a shorter period of time, although that would not allow for any kind of hiccup in the process. But it it can be completed in a shorter period. But I think that the window that we asked for and was provided, you know, ample time for any kind of issues or problems that would arise. This road was closed to, traffic, and, you have residents and emergency vehicles and things like that that need to access, on either, get on both sides. So that's why the pedestrian bridge was put in. But I guess if you plan on opening earlier and you don't finish, then it's going to cause quite an issue for everyone, and nobody's going to be happy if they have to sit there and wait. So
Okay, thank you. Next question is, were the PT ducts grouted?
Yes, they were.
Okay. Next question, what is the material infill for the micropile casings?
We did have a micropile grout in there. The 20-day compression strength was 4,000 psi, maximum water cement ratio 0.36.
Okay, thank you. Next question, were approach slabs or joints used at each end of the new bridge?
No, there are no approach slabs.
Okay. Next question, the planks supply eccentric loading to the girders. How to make sure the whole structure is stable? I guess that's where the struts come in.
Yes.
Okay.
It goes back to the whole construction process and the final tie-in with the curb. But we did address this turning into the roadway. Oh,
Right.
that's with that slide is applicable.
Yeah. Okay, thank you. Next question, any idea about cost premium compared to a decked I-beam system?
a deck and I-beam system was going to be very, very difficult to construct because we wouldn't have the freeboard. And this allowed, I guess, the maximum amount of freeboard for drainage. And so I guess trying to put in a girder bridge would require a pretty significant and long approach modification, because this bridge relies on line of sight for people to cross in the permanent condition, because it's a single lane bridge. And so there was no cost comparison made to a girder bridge.
Okay, thank you. Next question, how are the transverse beams constructed between abutments before the weekend closure?
Basically, the road was shut in the middle of the night, and they dug it out and dropped in rebar and poured it with a high strength, and then plated it, and then opened it up to traffic.
Okay, thank you. Next question, was there a topping used on those precast concrete planks or panels?
No, there is no topping.
Okay, thank you. Next question, would 18-inch thick, ultra high performance concrete, 70-foot span planks be viable and cheaper?
What was that again?
Would 18-inch thick, ultra high performance concrete, 70-foot span planks be viable and cheaper?
So you're talking about putting it longitudinally instead of transversely? Is that?
Yeah, that's what I think the thinking is behind the question.
I don't think so. Our experience with UHPC has, produced, I guess, pretty high cost differential, and it would require some, I guess, significant design changes, and that would be very difficult to, I guess, uh, compare at this point. But just the concrete itself for the planks would probably be more than the cost for this bridge.
Okay, thank you. Next question, what kind of concrete was used for the cast in place curb? Was it any fast cure or set concrete?
No, it was it's the 6,000 psi mix, 0.4 water cement ratio. We had the Cortec SRA and some fibers in there.
Okay. Next question, why did you leave the bridge as one lane only? And that may be related to the ADT, but that's the
No,
question,
this
why
bridge is
leave?
on the historic register, and there's a Hanalei Roads Committee that participates in any of the 106 consultations and with FHWA, and the state had agreed, I guess, previously that any kind of bridge replacement or modifications of these bridges, that the bridges would remain as single lane bridges.
Okay, thank you. Next question, do you normally use 6 KSI concrete or did the project require a special provision and development of a special mix?
That is typical of our projects.
Okay. Thank you. Can you provide more information about micropiles, scour measures, as there were no end bends built?
So there are rocks placed around the abutments. However, in case those are removed, there's also an additional measure with our steel casing that goes around the micropiles. So the bottom of the steel casing is below than any anticipated scour depths.
Okay, thank you. Next question, what vehicular collision load was used in the design of girders? How was the load transfer accounted for in transverse beam connections?
So we designed the girders for TL1 impact loading, vehicular impact loading. If we go back to that slide with the curb, you'll notice that there is a number 8 bar that is that connects the girder to the curb, and the curb is connected to the plank. So it transfers any hit load. The hit load goes into the girder, which transfers into the curb and into the plank, which then goes into the creep blocks and into the foundation. So James had a slide where there are creep blocks, these L-shaped creep blocks at the four corners of the bridge.
Okay, thank you. Next question, why was this kind of bridge selected as the replacement structure versus box beam or some other type?
Basically because we wanted to get the largest opening that we could to allow for any kind of storm flow. And this allowed the greatest freeboard.
Okay, thank you. Next question, did you have any issues with the use of micropiles? Or were they just selected due to ease of installation?
It was chosen because that was I guess that was what almost the biggest size rig we could get into the area to do the work. Um, a drill shaft rig, a power driving rig. The weights on those machines were prohibitive and could not get into the site.
Next question, weren't the wedges an actual impediment to fully fill with concrete the gap between the plank and the girders?
The wedges were removed at that point, so
Okay.
that the grout could be easily placed.
Next question, were there any big trucks expected to pass this bridge?
After the bridge was completed, there were some larger vehicles that were allowed to pass on a limited basis, tandems at the largest size,
Okay, thank you.
regular highway tandems.
All right. I think I'm at the end of my time. There may be a couple of outstanding questions which we will answer on the website. So with that, I thank you for the answers and I turn it back to Mary Lou.
Wow, what a great Q&A session. And of course, that was preceded by a great presentation. Thanks again, James, Eric, Gary, for sharing your Hawaii Waikoko Bridge Replacement Project, for your thoughtful responses during this Q&A session. Also, thanks to Paul and Jugesh for moderating the Q&A session, to Ali for managing the web room, and to all participants for your interesting questions today. We appreciate that. We look forward to your participation with us again for our next monthly webinar on Thursday, September the 15th. This concludes today's webinar. Thanks so much. Bye.